Hello and welcome back to another FE exam review. So I'm going to go ahead and go do some design problem. As I do a problem, try to understand it, and then I put another problem in there, then you will do it. If you're good practice, you need to pass this exam, you don't have any choice. All right, let's get to work. Here's the first problem. Okay, it says, what is the design load for a shortly reinforced concrete column whose surface load are shown below? Remember, when you're using concrete, you got to use the RFRD method, so that means you have to add your load based on ASCE 7, which you can see. One of the important things is for you to go on your FE handbook and know that in and out, because that's what all you're going to have in the exam. So this is very easy. If you look at the LFRD, there's two load combination will apply here. One of them is a PU is equal 1.4 times dead load, which is equal 1.4 times the dead load was given as 120 kips, and 1 times for that should give us about 168 kips. So that's one combination. Second combination says you got to use PU is equal 1.2 times dead load plus 1.6 times life load. So we're going to have 1.2 times 20 plus 1.6 times life load was given as 220 kips. And that's giving me the value of 496 kips. Then the next combination we have, it says, okay, we got a wind load. Okay, so we got another combination we got to consider, and that's going to be PU equal 1.2 times D plus 1.6 times wind load and plus 1 time life load itself. So it's 1.2 times 120. And 1.6 plus time W came out to be 150 kips, and plus life load 220. And that combination gives us 604, which that's the controlling load. And you look at these three different combinations, the code says the highest of these three will win. Well, obviously it's going to be this one, so that's your answer. Look at the next problem. This next problem we have, it says interior column beam for an enclosed frame structure have shaped, as you can see the shape on the screen, as shown. The concrete is a 5,000 pound concrete. The steel is about 60,000 pound. And what is the nominal moment capacity of this section? I'm going to go ahead and explain this step by step how we get to it. It really should take you less than a minute to do this problem if you know the equation. Your assignment right now is pause this video, go to the FE handbook, find out under civil engineering, go all the way down until you get to the reinforced concrete, review that for 2 minutes, then come back and you see with all the formula I put up here, they should be out of that book. Because when you take the test, that's all you have. All right, let's get to work. So the first thing I got to figure out is the effective depth. The effective depth is from the center of this rebar all the way to here. But if it's from here to here, it's 24 inch, so it's going to be 24 inch minus. They said this is a number 4 stirrups. And if you go back to the FE handbook, number 4 stirrups it's a ½ inch. So minus ½ inch, that's the stirrups. Then minus 0.5. Then minus the halfway between these two, the diameter of number 11 bar is 1.41. So minus 1.41 divided by 2, and that will give me 21.3 inches. Now we have that number, we're good to go. And then again, from a FE handbook, one thing we want to calculate beta 1, and that is equal, by looking at the equation, find it yourself, 0.85 minus 0.05 time f prime c minus 4,000, divide that by 1,000, make it a cube, basically minus 4 should be all right. So I get 0.85 minus 0.05 times 5,000 minus 4,000 divided by 1,000. And that comes out to be 0.8. So that's, again, from the table that is given to you from a handbook. I want to know what's the area of this number 11 bodies. So it's 3 of them. So we're going to say AS is equal 3 times, and the area for each one of those is given, 1.56. And that will give you 4.68 inch square. Now we're going to calculate the depth of the block, which is given to you, the equivalent depth of the stress block, compression stress block. A is given by AS FOI, divide that by 0.85 F prime C times B, which is equal, AS we already have figured out, 4.68 times, and if I just use the 60, I can use the other one as a 5, divided by 0.85 times 5 times, this was 12 inch. So your stress block comes out to 5.5 inches. Then you just plug an equation, really. Your moment that they're looking for, MN, that is equal ASFOY time, this marker is not making it, D minus A divided by 2. So AS came out to be 468 times 60's FOI of the steel, minus D came out to 21.3 inches, minus A divided by 2, minus 5.5 divided by 2. Check my math. I'm just going too quick here so we can get it. I get 5,208, and that's inch kip. The answer they're looking for is foot kip, so divide that by 12, and that is going to become 434.07 foot kip. All I did, divide this by 12. And there's your answer. Now here's your homework. The next problem, you're going to go ahead and do that. And then if you're the first person got to it, please go into my YouTube, where you're watching the YouTube, go to the bottom of the description, go ahead and put the answer down. And if your second person got there, just go ahead and say, yeah, I got the same answer. All right, let's get to work. We're going to go to the next problem. Okay, take a look at this next problem. We have this, let me bring it up. So we got this concrete beam, and they want to know what is the tensile reinforcement is number 4 bar, shear reinforcement is number 4 stirrups. What is the tensile strain in the steel? So if you go to your FE handbook, you know this is a depth of your stress block, and this is also the relationship between the stress block and a neutral axis depth. Or you can just go ahead and fix this up and come up with this equation, same thing. And then they give you this equation for the strain tension. It takes you less than a minute to do. Let's plug in. But we need effective D. We need to find D first, effective depth. So D is going to be equal, they said its depth is 24 inches. And then we're going to say, okay, let's take 1.5 inch cover, minus the stirrup B is another 1/2 inch, minus the half of the diameter of number 10 rebar, which is 1.27 divided by 2. 21.36. Check my number, please. So now we have that, and I'm going to just go ahead and calculate C right there. Let me use a different color. And I'm going to say C is equal, there's the equation. AS comes out to be 4 of them, 4 times 1.27 times 60, divide that by 0.85, and beta for that type of, 4,000, 5,000 pound concrete is 0.85 anyway. Look that up in your handbook, you can find that. And time 4,000 pound concrete, time B said it was 15 inch. So that will give me the depth of neutral axis is going to be 703 inches. Really, that's all I need because I'm going to go over here. So I'm going to say, okay, the strength is equal because time is the S in here. So 0.003 times D came out to be 21.36 minus 703, the whole thing divided by 703, and that comes out to be 0.0061. And you can say, me explaining it almost took me a minute. It should take you less than a minute to do so. So here's your job. You go ahead and do the next one while I erase this board. Okay, we're going to use basically the same equation. Just like last time, we're going to go ahead and find the effective depth. You should, by now, you should know that pretty good. And that was 20 inch minus inch and a half minus half inch for the stair minus it's number 9, so that's a 1 inch. That's going to be 1 divided by 2. So that will give me about 17.5. Now we have that. The next thing we're going to find is the size of our block, A, and that's from this equation here. AS comes out to be 3 times 1. That's a 1 inch, and times 60. Divide that by 0.85. And I thought it was 3,000 pound concrete, yeah. And multiply B is 12. So that will give us 588. And depth of my block is going to be right here. So C is going to be A divided by beta 1. Beta 1 is 0.85. This is basically this equation right here. Okay, you can put it together yourself. Think about it. So now that's going to come out to be, or not to be, 6.92. So that's the depth of our neutral axis. The next thing we're going to calculate is the ET. It's equal 0.003 time D came out to be 17.5 minus 692 divided by 692. So that comes out to be 0.0046. Now that's a bad number because it fell in between. It's in a transition. If you look at the handbook, go look at the handbook, and your ET is right now between 0.005 and 0.002. That means it's in a transition state, so the phi you got to calculate has to be using the equation to calculate your phi factor. And the phi factor comes out to be, this is equation 0.48 plus 0.83 times ET, which comes out to be 0.48 plus 0.83 times 0.0046. So now we have 0.86. That's our phi factor. And your Mn is given by this equation, same handbook, AS FOI times D minus A divided by 2, which is equal 3 times 60 times 17.5 minus 588 divided by 2. So that's come out to 21 inch kip. They want the answer in foot kip, so divided by 12, it becomes 218 foot kip. This problem, it says we have a rectangular reinforced concrete beam, has a simple span of 18 feet and a uniform distributed load of 5 kip per foot. The beam section is rectangular with 12-inch depth, 12-inch wide and 20-inch deep, 5,000 pound concrete, 60,000 pound steel. What is the required flexural reinforcement? So the area of reinforcement should be one of those. You gotta attack this backward because they already given you the answer. They say which one is it. So we're gonna go ahead and use those answer plug-ins, see which one come and work out. So we go from a high, and then we compare it, see what we're gonna get. All right, if you remember from a mechanic material, first we're gonna find the maximum moment. So maximum moment usually is given by, for uniform distributed load is WL squared divided by 8. In this case, it's going to be 5 kip times 18 squared divided by 8. So that will give me about 202.5 kip foot. Now we have that. And let's find the depth of the effective depth, which is basically, in here is just say h minus 2.5. Let's use that, make it quick. And since we don't have enough information, depth was what? 20 minus 20.5, and that's 17.5. Let's try the answer of 4-inch, see if that was going to work. Okay, let's say if AS is equal 4-inch square, therefore I'm going to come back, calculate my stress block. Then my stress block is going to come out to 4-inch square time 60, divide that by 0.85 time, it's a 5,000 pound concrete, yeah. And then time B was 12-inch. All right, double check my number, please. And that'd be 4.7 inch. Okay, so now we have that. And we say, okay, I erased it. The equation for the moment, MN, is equal AS time FOY time D minus A divided by 2. So now I have 4 times 60 times 17.5 minus 4.7 divided by 2, and that will give me the answer of 303 foot kip. So the design capacity, the design moment capacity is phi times MN, and the phi for a beam is what, 0.9. So I have to make 0.9 times 303, and that will give me 272.6 foot kip. And our maximum when we come out to 202. This will work, but are we way over designing? So that's for the 4-inch, which is still bigger than 202.5. And let's go ahead and try the next one down. I'm not going to go 2.5. Let's go for 3 inches. All right, let's change color here. See one of these working. Well, say AS is equal 3-inch square. And doing the same exact thing we did before. Our A is going to come out to be, instead of 4, we're going to have 3 times 60. Divide that by 0.85 times 5 times 12. 3.53 inch. So our MN come out to be ASFOY, so it's a 3 times 60 times D, which was 17.5 minus 3.53 divided by 2. And that will give us a 236. foot kip, and if I multiply phi times MN, 236 times 0.9, and that will give me 212. This is closer, which is bigger than 202. So this one won't. You go ahead and try the other ones. See how it works. Okay, take a look at this last problem on a concrete. So we're going to go ahead and design a square tight column to support a dead load of 130 pound kips and 180 kip for life load. It says initially assume 2% longitudinal steel. F prime C is 4,000 and Fy is 60,000. So they already told us it's 2% steel, makes it easier. So we're going to go ahead and just plug in. First, we're going to find out our PU, which is a 1.2 times dead load of 130 plus 1.6 times of 180. And that should come out to 444 kip. Plug in those number up there. Phi times Pn comes out to be phi for column is 0.65 times 0.8 times 0.85 times the concrete was 4,000 pound. Okay, now the area, it's going to be time, we don't know, we're looking for area. And they said the steel area is only 2% of the gross cross-sectional area, 0.2 Ag. That's what they told us. It says 2% steel. When it says 2% steel, that means AST is equal, area of the steel is equal 2%, 0.02 times the total area. So plus 60 times AST, which is 0.02 Ag. Let's go ahead and plug in the calculator. Your Ag going to come out to be 188.4 inch square. That's it. Now we're going to go ahead to go to steel design. Take a look at this problem. It says find the plastic moment capacity of the build-up section. As you can see here, an Fy is 36,000 steel KSI. So they want plastic moment capacity. First, we got to find a plastic neutral axis. And this, because this is the whole thing is a steel, that means the you get the area of the whole steel, and halfway through, it's going to be half of the area above plastic neutral axis should be equal to half of the area below the neutral axis. So let's just go ahead and calculate the area of each one of them right away. This one, if you call this one 1, 2, 3, I'm going to say, okay, A1, it's going to become 10 times 2, that's 20 inch square. And A2, it's going to be, oh, it's not going to be easy. This is a 3/4 inch, right? Yeah, it is. So it's going to be 18 times 3/4 inch. I think I might have that. 13.5. Check this number. Inch square, and A3, it's going to be 12 times 1. 12 inch square. So now we have all the three area. And if we add all these three area up, and we're going to get the answer of 45.5 inch square. So the total area is 45 square. I want to know where is this neutral axis going to be. Plastic neutral axis, P and A. All right, I don't like this color. Let's come back in here. And we're going to say, okay, if half of that, it's going to be 45.5 divided by 2. If I take this out, which was 20 inch square minus 20 inch square, and then that will give me 2.75 inch square. So I need a 2.75 inch square from here. So what is this distance I'm looking for? This distance right here. All right. So I'm going to say, we know that's a 3/4 inch. So I'm going to say 2.75 is equal. And that's going to be same as this distance y, which I don't know, y. And that's going to be time 3/4 inch, which is 0.75. 0.75. Therefore, my y comes out to be 3.67. Okay, so that's a 3.67 right here. And if you add this to this distance, it's going to become 5.67. And you know that's, you can figure these distances out quickly. 5.67 minus, my numbers are there. I think I got them. So now we want to find the plastic modules section, which is a Z, and that's going to be 6 section modules. And that's going to be basically the summation of all the area, first moment area about the neutral axis. So that's going to be, or we can write it down as a summation of AI times YI. Again, you go to your steel design handbook, make sure you know that stuff pretty good, because that's the only thing you're going to have. Study it. All that stuff is in there. All right, summation area. I'm just going to start from the bottom. That was good, 12. All right, and the distance from the center to here is what? If it's 15.33 minus ½ inch, that should give me about 14.83. All right, and then now we're going to go ahead and do this section by itself, just this section, okay? That area, and that's going to be the area of this going to be, we got to figure the area out first. 14.33 times 3/4 plus the area of that's going to be 14.33 times 0.78. That's just the area of this, and multiply the y is going to be from center of this to here. So it's a 14.33 divided by 2. That's it. And now we're going to go ahead and do bottom shape plus. We know that's a 2.75. The area we came up with, it came out to 2.75 already right here, so I don't have to calculate the area. 2.75, and that's going to be multiplied by this half of this distance from here, to this neutral axis, which become basically 1.833, and then plus the last one, which is this one right here. It's a 20 inch time the distance from center here to there. It's going to be, that's a 2 inch, so it's going to be 467. So now that comes out to be 353.4 inch by power 3. Again, look at your steel handbook. Your plastic moment capacity is equal Z times FOI, ZX times FOI, which is equal 353.4 times 36. And that will give us basically MP is equal 1060.3 kip foot, and there's your answer. Okay, now here's the deal for you. I want you really go ahead and interact with me and go to the below the description on my video, write your comments, and you're going to do the next problem right there that you see on the board, and hopefully you'll be the first one to give the solution, and if somebody else has it, go ahead and do it. All right, while you look at that problem, it should take you less than 2 minutes. Keep practicing, because practice makes it perfect. You need to pass this exam. Let me erase the board. We're going to go do the next problem. This problem, it should take you less than a minute to do this one. The top flange of simply supported beam, 20 feet long, is continuously braced against the buckling, so that's good. We don't have to worry about LB. By supporting the slab, if the service load is uniformly distributed loaded, they got a dead load of 2 kips, a live load of 3 kips, and a wind load of 2 kips. What is the lightest W section which satisfy use Fy equal 50 KSI? Again, you have to use your handbook. Go to the handbook section, steel design. Combination, find the load. There's three different load combinations we'll apply here. WU is equal to 1.4 times dead load. That's 1.4 times 2, which is equal to 2.8 kip per foot. Load number 2 combination is going to be WU is equal to 1.2 times dead load plus 1.6 times life load. And that's going to be 1.2 times 2 plus 1.6 times 3. And that gives us a 7.2 kip per foot. Load combination number 3 is going to be basically plus 1 times W and plus 1 time life load. So that's going to be 1.2 times 2 plus, the wind was 2, plus 2 plus 3, and that's equal to 7.4 kip per foot. This one controls. The next we're going to find out what's the required plastic section modulus. Required Z is equal, and that's going to be basically given formula from your handbook, 0.9 mu divided by 0.9 times FOY, and mu came out to be, we don't know that. So let's calculate mu first. Mu is equal WL squared divided by 8. You know that. That is 7.4. They said it was 24 squared. Divide that by 8, and mu comes out to be 370 foot kip, or 440 inch kip. Can we? I'm going to go ahead and say, okay, mu is a 4440.9 times. They said Fy for this one was a 50, and that is equal 98.7 inch cube. So from your handbook, I think it's page 283, this will give us W 18 by 50. That's it. Again, should be less than 2 minutes. So W 16 by 67 beam has a simply span of 30 feet. Carries a uniform distributed load over the entire beam. Steel grade is A992. 50 KSI. The compression flange of the beam, the top of compression flange lateral support is it's supported at the mid span only. Ignore CB. The maximum factor load is, the beam is what? So we know one thing here, that our length of unbraced is equal 30 divided by 2. It's a 15 feet. That's an unbraced length. And from Z table, and it's in your handbook, I don't know what page it is, you can find it. For W 16, that's a nice W, by 67, we have phi b time mn is given as 488 foot kip. And then, same table, give us LP is equal 869. LR is given as 26.1. We see that. Then we have phi BEF given as 10.4. Okay, once you know this problem and you see one like it, it should take you take you 5 minutes to learn it, take you a minute to do it. So since LB is our LB and brace length is 15 feet, this is our LB, L and braced, and 15 feet is between these two numbers. And then we're going to go ahead and say, okay, the moment capacity is given by phi MP as phi MN minus LP. Let's plug in. So I got phi MN is equal, and that plastic one we just found out was 488, and minus this one came out 10.4. It should be a phi B here. 10.4 times this was 15 minus 8.69. So that will give me 422.4 foot cube. So now we know that is phi MN, and we know MU is equal, that's due to the applied load, WL squared for uniform distributed load divided by 8, and therefore W is equal, or MU basically came out to be right here 422.4, and if I correct this one, it become W equal 422.4 divided by 30 square, that's L, and multiplied by 8. Basically took this and MU is equal to that, and that will give me 3.75 kip per foot as your answer. So while doing this problem, I'm going to erase this board. All right, next problem, it says, what is the nominal compression load capacity of a 12W, W12 by 50 column, whose governed slender ratio is 90, and use Fy equal 38, KSI, and Fu is equal 55. Okay, so this is, we're going to go do some column work, and let's get to work here. And W12 by 50. So we're going to go ahead and look at your, this is a PPS 40. We're going to go into your handbook right there, and we're going to say for W12 by 50, we have the gross cross-sectional area come out to be 14.7 inch square. And I think this is a, look at handbook page 82, 282. And from there you want to know there's a, for the critical buckling, what is your ratio going to stand for? And so we're going to say, okay, what is 4.71, it's on the formula, square root of E divided by FOI, and that comes out to be 4.7 times, steel is 29,000 KSI, modulus elasticity, divided by, I think the FOI was 38, yeah. And that will give us 130.1. So we less than that. We're going to use the Euler buckling equation. In the Euler buckling equation, remember FAE is equal pi squared E divided by KL divided by R squared. So that will going to give us pi squared E is 29,000 KSI. Divide that by 90 squared. I'm having an issue with the marker. So that comes out to be 35.34 KSI. And our KL over R is less than 130. So that tells us the critical stress is going to be, look in your handbook, this equation, find that 0.685 by power FOI over FAE, and time FOI. So we got 0.685 by power of 38 divided by 35.34, and the whole thing multiplied by 38. So that gives us 2423 KSI. Then the nominal load, Pn, is given by this equation. The load capacity for the column is basically that multiplied by the gross cross-sectional area. So I got 24.23 times the 14.7. So that comes out to be 356 kip. That's your answer.